So we know how to solve systems of equations using substitution and elimination. Now we've learned a matrix technique that involves the inverse. And the last technique that we're going to use with matrices to solve systems of equations is Gaussian elimination and eventually Gaussian-Jordan elimination.
Is it named after Michael Jordan?
It is not named after Michael Jordan. Now, if you had this very simple systems of equations, one of the easiest ones in the world to solve, what would you solve for first, x or y? Oh, probably solve for y first, since it's already given to be 2. And then what would you do with that 2? You would plug it back into the other equation and find out what x is. Now, we're going to introduce the idea of an augmented matrix here, although I have mentioned it before. What an augmented matrix is your coefficients matrix and your solution matrix put together with a line in between. On your calculator, that line doesn't show up. You just make it a 2 by 3 matrix. But when you look at this, what it stands for is one column stands for your x values, one column stands for your y values, and the last column stands for your answers. So if you have a matrix that looks like this with a 0 and a 1, well, then you know right away from this that y is equal to 2. So if we have a matrix that doesn't look like that, what we do is we change things around to make it look like that. So this type of matrix with a 0 in the bottom left-hand corner, and if it's a 3 by 3, you'd have 3 zeros in that bottom left-hand corner, is called reduced echelon form.
You have negative 2y, you put negative 2 as your coefficients.
Yes.
Yeah, it's not what you said.
What did I say? Oh, I said reduced. No, it's not reduced row echelon form. It's just the row echelon form. We'll look at reduced row echelon form later. So this idea of getting it to this row echelon form is called Gaussian elimination. So how do you do it? Well, first you create your augmented matrix, and then we use something called elementary row operations, which means you are allowed to interchange any rows you want, multiply a row by a non-zero number. Multiplying by 0 isn't very helpful because it just gets rid of everything. And then add a multiple of one row to another. So we'll see what that means. Okay, so here's an example. Here's our first systems of equations. If we set this up as an augmented matrix, we would have 1, negative 2, 10, 1, 4, 16. Our goal is to make this bottom left-hand corner a 0. Okay? So what I'm going to do, and the way that I'm going to show my work, is I'm going to say, I'm going to change row 2 to equal, and what I can do to row 2 is any one of these elementary row operations. And what I'm going to do is use number 3. I'm going to add a multiple of one row to another. And we could add to this add slash subtract. Of course, adding a multiple of negative 1 is the same as the idea of subtracting. So what I'm going to do is I'm going to take row 2, and I'm going to make row 2 equal row 2 minus row 1. So I've set up my instructions on the arrow, and then I write the new matrix after I've done the operation. So row 1 hasn't changed, so it's still 1, negative 2, and 10. But row 2 is now row 2 minus row 1. So if I take row 2, 1 minus 1, this will become 0. 4 minus a negative 2 would become 6. And 16 minus 10 would become 6 as well. This is now in row echelon form. this tells me that 6y is equal to 6. And y is equal to 1. I can therefore take my first equation, which is x minus 2y equals 10, add 2 to both sides, and x is equal to 12. Yes?
You're literally, when you're subtracting the two rows, you can do the exact same thing with the system of equations.
That's right. It's the elimination technique.
You go, but what's the point? You go x plus 4y equals 16. Because when it gets more complicated, more dimensions back.
When you have a 4...
But you're figuring out the logic the same way. So
Yes.
if you got the same logic, you can just do it with the same system of equations.
You could. But the idea will be that this, as we get into bigger ones, you know when you solved with elimination with a 3 by 3, you'd eliminate one variable and have two equations and then have to take those two equations and eliminate them? This keeps it all together in one system. Plus you can put it in your calculator and check it, but which is handy. Now once we're done, we can check. Does it work? Is 12 minus 2, 10? Is 12 plus 4, 16? Yes. So we know that these answers are correct. Now, at times, the numbers don't work out as nicely. So here I have 2, negative 3, negative 2, 4, 1, 24. I want to get that bottom left-hand corner to 0. So how could I do that? I could take row 2 and make it equal to row 2 subtract 2 row 1s. And now we rewrite the top one because we haven't changed it. And this is where, with matrices, if you make one little mental math error, it throws everything off. So here we're going to go 4 minus 2. That'll make this 0. That was our goal. 1 minus 2 times negative 3 will be 7. And 24 minus 2 times negative 2 will be 28. So now we know that 7y is equal to 28, so y is equal to 4. And plugging that back into the original one, 2x minus 3 times 4 equals negative 2. 2x equals 10. And x is equal to 5. Yeah, it's supposed to be a nice looking 4, but it did not turn out that way. So, and if you check them, sure enough, second one works. 10 minus 12 is negative 2. Both of them work. So what does it allow you to do as compared to before? Before, you would show that you would multiply everything by negative 2, have to rewrite it on top of each other, and then add. Maybe in this situation, you can see you're doing all of that at once. A little bit shorter, maybe not that much. Okay, one for you to try. What do we have to do first? We have to do a little bit of rearranging so that it fits an augmented matrix form. There's one, and I'll put up the next page answers as well, see if you can do that one. If we are working with the 3 by 3 and we want these zeros, we think back to how we do things with elimination. If you were doing things with elimination, what you would do is you would choose, often we would number these equations 1, 2, and 3, and you would choose a variable to cancel completely, right? Either get rid of all your x's, get rid of all your y's, or get rid of all the z's, so that you get down to 2 equations with 2 unknowns. The way that this shows up here in this form is, These two zeros here represent getting rid of the x's and leaving you with two equations with two unknowns. So what I've circled in red there will become our first step. Before we find this last zero, we need to cancel out those zeros first. So here's what I did. First of all, I switched row 2 and row 1 because I like having a 1 in my top left-hand corner. It makes row multiplications and subtractions really easy to work with. So I put the 1s across the top, just switched row 2 and row 1. And then I made these two zeros first. How did I do that? Well, I took row 2 and made it equal to row 2 minus 3 row 1s. And now that there's a 1 there, there's very easy math to cancel. Right? With a 5 and a 3, it would be hard to cancel out because of the multiplications you would have to do. Okay? It's possible. You could multiply, you could multiply row 3 by 3 and row 2 by 5, and they would cancel out. But there's a lot of mental math that's going on there, and that increases your chance of an error. Row 3, I just took row 3 and minused 5 row 1s. Doing that gives me zeros in both of those places.
And now they can operate on each other's steps.
And now you can operate on row 2 and row 3 without changing those zeros that are out in front. All right, so right here what I did is, again, I guess I should write this in, I changed row 2 to equal negative row 2. Do you see how I had negative 1, negative 7, negative 32? By multiplying row 2 by a negative, it just made them all positive. So that is, as far as our operations go, right, where is that? This right here, right, multiply a row by any non-zero number. There I just multiplied by a negative 1. My next goal is to get this to be a 0. I can do that now by taking row 3 and adding 6 row 2s. The key here is I'm using row 1 and row 2 because these are both zeros. When I add 0 to 0, they stay both zeros. Okay? And so adding these together, 42 plus negative 4 is 38, and here we've got a little bit of bigger numbers to work with. 6 times this will be 192 minus 2 is 190. And we finally got the bottom corner here all to be zeros. Now we can set up our equations. 38z is equal to 190, so z is 5. You can then use the second equation, y plus 7 times z is 32 to get y is negative 3. And then finally go back to your first equation and plug in y and z and find out what x is. So that gives us our solution without having to do all the elimination. So what did we do when we solved this with the elimination? You did this first. Chose two equations and got rid of one variable, giving you a system here in this green box. This is a system of two equations and two unknowns. And then what did I do is I used elimination again to get to a system with one unknown and one equation, which is really nice. And then it simplifies. Okay?
So if it was a 4 by 4 matrix,
all right, there is your next one.
Okay,
So I would, again, switch things up.
could I just, like, if I was given this question, could I just write, like, just start?
Row 2 is your first one, that's fine.
Yeah, so just write it in.
Yeah.
Okay.
I would do that too. This one, Because this has a coefficient of 1 here, I like to put that one up front.
Oh, we're trying this one right now?
Yeah. Here's a check. If you got those zeros first, and then there are your answers. But if you want to check your first set of zeros,
What's x again?
oops, x is equal to -1.